Because it is the beginning of the semester, I have to do census, which is basically take attendance. So those of you guys who are online, if you could do me a favor and in the Twitch chat, basically just respond when I call your name. Okay, but first, let me get to the list here. Make sure we got everybody. All right, Mr. Borden, you're here. Farden, are you on Twitch with us? Hopefully. Yep, okay. Farden, you're here. Excellent. Mr. Hurt, you're here. Mr. Kim, Mr. Lee, Mr. Michalski. Zane, are you with us on Twitch this morning? Let's see who all's in. Don't see Zane just yet. We'll give him a second. Let's see who else. Dang it, if it would help if I could get to the correct window. Okay, so let's see. Zane, Mr. Snyder, you're here. Mr. Trapp, you're here. And Coy, are you with us on Twitch this morning? We'll give him in a minute also. Okay, well let's get to what we're here to do today, which is let me get to overlay so I can see what I'm doing. So I'm going to switch over to the iPad, and yeah. So we're going to do some more trig stuff this time, and for lack of a better way of putting this, the stuff that we did last time was we looked at, if you had an integral that involved a bunch of trig stuff, how did you make some sort of clever substitution or something to get rid of the trig stuff? Today will be sort of the opposite. If you have an integral that doesn't look like it has any trig stuff in it, then maybe actually deliberately putting some stuff in that is trigonometric is actually a good idea. Okay, so it sounds like it would be a train wreck. We're going to make something a little bit more complicated, but perhaps maybe we could do something clever. Okay, so let's consider a problem that we might care about that's sort of geometrically inspired. So let's say we had this, the integral of 9 minus x squared, and it doesn't look like you guys on Twitch can see the iPad, and I'm not sure why that is. Oh, that's because I'm not on the right device. I'm sorry, guys. Okay, yeah, that's my bad. I had it set for the direct connection iPad, not the Elgato capture card iPad. So, okay, there we go. Sorry, Farden. All right, so we've got this integral here. Integral of square root of 9 minus x squared. Do we have a technique that can deal with this integral yet? What's the temptation here? Yeah, go ahead, John. Okay, if we tried to do a u substitution, right, that's a tempting option. The only real option there would be u equals 9 minus x squared. And that'd be great, except what's du? Negative 2x dx, and we don't have an extra factor of x there. Okay, so that's not going to work, unfortunately. What's the other trap answer? Well, isn't the square root of 9 minus x squared 3 minus x? Can you do that? No, you most certainly cannot do that. So we're kind of hosed. Now, why might we actually care about an integral of this form in the first place? What does this describe geometrically, perhaps? Right now, nothing, but square root of 9 minus x squared, what does that make you think of? Makes you think of Pythagorean theorem or, sort of relatedly, a circle, right? So the square root of 9 minus x squared would describe the top half of a circle. And if we had bounds on this integral, then that would be basically saying, find me part of the area of a circle, okay, whatever part of it that we actually are interested in. The problem, of course, would be that we don't know what this antiderivative is. Okay, so the trick that we're going to use is to sort of say, all right, if this thing looks like it's involving a circle, or maybe not necessarily just a circle, but a term that's sort of vaguely Pythagorean in look, right? So would you guys agree that the square root of 9 minus x squared looks Pythagorean in the sense that if we had a right triangle and we knew two of the three sides of it, then the third side might look like this. Yes? Okay. So here's what I'm going to do. I'm going to think of, imagine that I have a right triangle, and let me just put some angle here. Then which sides would be which for this 9 minus x squared to appear as a quantity? Okay, so I want to put an x somewhere, right? And the way that I choose to do that is to put, I'm going to put an x there and a 3 there, okay? What would that make the third side, the missing side by Pythagoras' theorem? Yes. Okay, which is something that we clearly have going on. Okay, so what I'm going to sort of do is think, all right, this triangle might be a useful tool in working with this integral. Okay, now we already said that some of the options that some of the techniques of integration that we already have, what do we have? We have U substitution, we have integration by parts, and we have, if there's trig functions in it, we can do, basically play games with trig identities. We already said U substitution's out. Integration by parts probably also out, and there's no trig there, so what we did on Friday doesn't help. But what I want to do is think about this triangle a little bit, and how else could you write x? Okay, you're mumbling and I can't hear you through a mask. Huh? Okay, that would be tangent of theta, right? Okay, so we could, let me erase that. So we could say, well, tangent of theta would be x over the square root stuff. But why'd you pick tangent? Okay, could you have picked a different trig function that also includes the x? What would have been a simpler one? I mean, what you said is not wrong by any stretch of the imagination. It's just not as simple as we can get it. What other trig functions do we have at our disposal? Cosine and sine. All right, so if we did cosine, oops, then it would be the adjacent over the hypotenuse, which would be this, or if we did sine, it would be that. Okay, so a couple questions from online here. Does this equation only work if there's a right angle in the triangle? Let's maybe think about this in reverse. Think about it more as I'm constructing the triangle of this form that is a right triangle, because I have an integral that sort of looks like it would involve that. So maybe I'm putting the horse before the cart, or whichever way it's supposed to. Which goes first, the horse or the cart? Usually you put the horse first, right? And then okay. Yeah, so I think, Jack, that's kind of the way I'm thinking about it. Is that I'm choosing this triangle because the integral looks the way it does, rather than starting with the triangle. Okay, so of those three trigonometric expressions, so I've got tan theta is x over the square root stuff, cos theta is the square root stuff over 3, and sine theta is x over 3. Which of those would you guys say is the simplest in form? The sine theta one. Okay, so let's pick that one, and I'm going to rewrite it in this form. Okay, so x in this case would be 3 sine of theta. Okay, why did I do that? Does this remind us of something that we did last week? I guess it was Wednesday, maybe Monday, I don't remember. Monday. Well, we did some spicy u substitutions, right? Where rather than finding u as a function of x, we started with that, and then we said, oh, but I could also think of x as being a function of u, right? In a sense, that's what I've just done here. I've said, suppose that x is 3 times the sine of some quantity theta, okay? If that's the case, what's dx? Yes, John? Uh-huh. Okay, so let's return to the integral where we started. We had this. What was it? 9 minus x squared, sorry. Okay, well, if I'm just chose to substitute x is 3 sine theta and dx is the 3 cos theta d theta, then this integral is the same as that. Okay. This, by the way, is why I've always been such a stickler on the dx or d theta or whatever, because what happens if you forget the 3 cosine theta here and you just magically turn dx into d theta? Well, then you're missing a 3 cos theta in this case, which is going to turn out to be important. Okay, does that make sense? Okay, so be careful and don't forget the entire differential. Okay, now that I've got it this way, what can we do next? Yeah, we could. I'm actually going to wait on that. Okay, because if I did a u sub, guess what you would do? You would get right back to where we started. Because if you said u equal, oh, I'll let u equal 3 sine theta, then du is 3 cos theta d theta, then the integral is the square root of 9 minus u squared du, which is precisely what we started with. Okay, so nice try. Play again. I mean, that works, but it's not helpful, right? Could we do some trigonometry foo with this stuff underneath the square root? Yeah, because isn't this the same as that? And isn't that the same as that? Okay, so I just basically expanded and then factored, and then why did I do that? Well, what is 1 minus sine squared? It's really cosine squared, right? So what I have here is the integral of 9 cos squared theta Okay, now here's where there's a minor technical point. What is the square root of cosine squared? Then that's not quite plus one. It can't be both, right? Because then square root wouldn't be a function. Yeah? Okay, true. That's not what I meant. Okay, so how could you simplify? So, like, what's the square root of x squared? Maybe would be a better way of putting it. X. Okay, but it's actually technically absolute value of x. Okay, however, um, because technical reasons, I can blow off the absolute value here, and maybe I'll talk more about why later. Okay. Um, good. And yeah, Farden, that's exactly where we're about to go. So now we have the integral of 9 cosine squared theta. Do we know what to do with that? Yes? Right. So we're going to use the double angle formula from last time, and I'm going to write this like so. Okay, so inside the integral is the identity that Jack just suggested, um, which was the power reducing identity from last time that turns cos squared into something involving cos of 2 theta. Okay, that's a little bit easier than uh, because we can actually integrate it this time. And then I just threw the 9 out front for cleanliness. Okay, let me actually take this, actually, and copy. Okay, I'm going to have to move on to a new sheet here. So are we cool up to this point? So let me just pause and see if we got any question preguntas and or fragens. And looks like we're okay on the chat. We've got, let's see, Coy, looks like you're here finally. Zane, are you with us? No, I guess RHS Jack. I don't know who that is. So from cos squared to that was one of the identities we used last time. So cos squared theta is 1/2 plus 1/2 cos 2 theta, right? So that is that the sheet I gave you? Yes. That is, yeah, it's a rearrangement of that one. Um, and I thought they were on here in a different spot. Yeah, it's just a rearrangement of that identity. Oh, here it is. Right. I mean, they're the same identity. It's just an algebraic rearrangement of it. So, yeah. Okay. So I'm going to move that, go over here, and then I'm going to paste. Oh, isn't modern technology fabulous? Um, okay. So that's what we had at the last step. Can we go ahead and integrate at this point? What would we get? Well, The 9/2 is going to become 9/2 theta, right? Here's where we do have to be a little careful because what's the variable with which we're integrating this time? We're now doing things in terms of theta, not in terms of x, right? So it's not 9/2 x, it's 9/2 theta. Good? Okay, so just be careful. When it's 2 in the morning and you're in a hurry and tired, that's something you will mess up. Okay, so 9/2 theta, what's the integral of cos 2 theta? Do you guys agree that it'd be 1/4 sine 2 theta? Yes? Okay, are we done? No, because we're never done. Yes, exactly. Why are we not finished? We're finished integrating, yes, but why are we not finished with the problem? Right, theta was something we introduced that's auxiliary to the problem. The original problem had nothing to do with theta. So we have to convert everything back in terms of x, and here's where we're going to have a little bit of fun. Okay, so let's go back to what was the relationship between x and theta that we had in the beginning? Mm-hmm. The relationship we had was that x was 3 sine theta, or equivalently, sine theta was x over 3. Okay, so either way. And I'm going to go ahead and draw that triangle that we used a moment ago. Um, there. Okay. So that's what we use to get started on this problem, and that's how we're going to convert everything back. So I have in my integral, or sorry, oh, thank you, Coy, yes. It's 9/4, not 1/4. I forgot yes, forgot the 9 that was out front, so that's fixed now. Thank you, Farden. Um, okay, so let's see, uh, the relationship we had there was that x was 3 sine theta, and now we've got things in our answer that are in terms of theta, and so we're going to have to go back to this triangle and that original relationship to get started. Okay, so let's start with the first term. What is theta? Yeah. Well, I can invert the trig functions. Okay, and this point here is, you remember a minute ago when I said, trust me, I'm a doctor? That's subject to the exact same trust. Okay, and I will talk about why it's okay to do what I did, but for the moment, just take it on faith and we'll go back and reveal those mysteries later. Okay. All right, do you guys buy that? Right, that you guys remember having the inverse trig functions back in high school and you're Gucci with those? Yes? All right, so that's one. But then what are we going to do with sine of 2 theta? Well, look at my triangle. Does my triangle have the angle 2 theta in it? No, it has the angle theta in it. Okay, so I need an identity. You guys happen to remember this one off the top of your head? Okay, so here's yet another identity that we need to use. Okay, this is one of the double angle identities for sine. Now, previously we'd used the double angles for cosine, but we never actually used the one for sine until right now. Turns out sine 2 theta is 2 sine theta cos theta. Now, why is that particular identity or the form of that identity going to be useful for us? Right. Okay, so now we have turned the problem into from a trig function of 2 theta into a couple of trig functions of theta. But I know a lot of things about theta because I've got a right triangle that involves theta. Okay, so in this case, what is sine of theta? Or, sorry, that's not what I meant to say. I meant to say sine 2 theta. Well, what is sine of theta in that triangle? This is actually the substitution we started with. Yes, Jack? Right. Okay, so I've got, let me put the 2. Then I've got sine theta was x over 3. And then I also have cos theta. Well, what's cosine of theta in that triangle? Yeah, the square root stuff all over 3. Oops, that is the worst looking 3 ever. Okay. All right, so now we've got it down to there. Oh, and then my plus c, of course. Okay, so let's sort of pause here and make sure that we have all the pieces accounted for. Okay, so when we integrated, we ended up with 2 terms, a theta term and a sine of 2 theta term. Okay, we solved for theta using the substitution we started with. So we said if x was 3 sine theta, that was equivalent to saying sine theta was x over 3. That was the simplest of the 3 trig relationships we noticed. And so we could solve for theta in terms of x by just inverting. Now, could I have used arctangent or arccosine there? Sure. The term would have just been a little bit more complicated looking. Okay, so I chose to use the one that was the simplest looking, and arcsine in this example was the one that fit the bill. Um, okay, so okay, Farden, I think you've made either an algebra mistake or you're getting the 3 over 2x. So is the x in the denominator or in the numerator? Um, okay. What else could we do to simplify there, though? I mean, lots of stuff, right? So what's going to happen here? That's going to cancel. That's going to cancel partly. So we'll get what? Um, just x over 2. Just that. Let's see, Farden. Okay, so 1/2. But you're going to have an inverse trig function in there somewhere, Farden, because from the theta piece. Okay, so subject to my bad handwriting, that should be what we have. Now, how do we check our answer, by the way? Yeah. Sighing doesn't check the answer for you. Yeah. So if we take the derivative of this thing, we should get back to, oh, I see, Farden, what you're up to. Okay. But should be a square root there. Um, so yeah, we'd have to take the derivative of this. In the second term, the 1/2 x squared or 9 minus x squared, we'd have to use the product rule and the chain rule. It might get a little messy. And then for the first term, we'd have to remember what the derivative of arc sine was, okay, which is not something that I expect you to have memorized. Um, the only inverse trig function that I think is worth memorizing its derivative is arctangent, for reasons that we'll talk about on Wednesday. Um, okay, so yeah, that's how we would check this. Um, for something nasty like this, you could just pop it into Mathematica or Wolfram Alpha and kind of just have it check there. But do you guys believe me that I'm not lying here? Yeah. Okay. All right. So let me return actually to the technical question as to why should you trust me? And it's not just because I'm a doctor. If we go back to the very original problem there, and we think about the quantity 9 minus x squared, um, x could be positive or negative in that expression, but what's the domain that we're sort of dealing with? What values of x are permissible? Yes. Uh, well, what about x? Could x be negative? Sure. Okay. So what numbers, what's the domain of the function we're integrating? Now, x can't be just any old negative number. It's only a specific pile, right? So, okay, let me rephrase the question. What's illegal when it comes to square roots? Square roots of negative numbers, or at least it's illegal in this class because what happens when you take the square root of a negative? Hmm? Yeah, you get imaginary stuff. Okay, can you do calculus with imaginary numbers? Absolutely, and it is a blast, let me tell you. Okay, but that is most certainly out of the realm of this course. That's called complex analysis, and we're doing Calc 2. So you guys will get there, those of you who want to be math majors. But, so the quantity 9 minus x squared cannot be a negative number. It can be 0, it can be positive. The biggest it ever is 9, right, corresponding to when x equals 0. The smallest it ever can be is 0, corresponding when x is plus or minus 3. Okay, so the domain of the function there is between -3 and 3. Okay, and that is why I didn't have to have the absolute value and stuff earlier, and why this trigonometric substitution is valid in the first place. Okay, because if x is a quantity between -3 and 3, what is x divided by 3 going to be? A quantity between -1 and 1, which means I can think about it as being the sine of some angle, right? Because what sine theta always returns an answer between -1 and 1, where theta, the angle, is between what? What are the range of theta here? So there's two answers to that. Um, the range of theta would be between, um, you could say, well, it could be any old angle, okay? But in order for me to talk about arc sine, I do have to be a little bit careful. Okay, so the reason that this all works and is kosher is because the problem that we started with inherently had a domain restriction on it. And so that's what allowed me to kind of throw this trig function in out of thin air. Okay, does that kind of make sense? Sort of. It's a technical point. I'm sure it'll sink in. Theta can, in this case, let's see, it should be for Arc sine, it should be between negative pi halves and pi halves. Okay, corresponding to an angle in quadrant 1 and 4. Right. Okay. Um, yeah. Okay. Um, okay. So, um, what other expressions could we see? So we looked at this original expression, 9 minus x squared, and said, oh, that reminds me of things that we see when we apply the Pythagorean theorem. Okay. What other things could we see if we applied the Pythagorean theorem, right? So what else looks sort of Pythagorean-like? Well, okay, so let me rephrase the question. The whole point of Pythagoras' theorem is to do the following, right? You know two sides of the triangle, right triangle. You want to know the third. Okay, so there are, let me come over to a clean sheet here. There are three situations we could find ourselves in if we know two of the three sides of a triangle, but not the third. Okay, so the question is basically which one don't we know? That's equivalent to saying which two do we know? Yes? Okay, so if we know the base and the height, great. If we know the base and the hypotenuse, different situation. If we know the height and the hypotenuse, different situation. Okay, now which one did we have in the example that we've just dealt with? We had this one. Okay, so we had that situation. Can I use the letter A instead of the number 3? Is that okay? Just to represent that, well, maybe it'll be 4 in a different problem. Okay, so let me erase this and just think of that as being an A. Okay, so if we knew the height and the hypotenuse, then we'd have that. Okay, what about if we know the base and the hypotenuse? Well, what situation would we be in there? Okay, for that one, I'm actually going to switch where I put the X and where I put the A for reasons that'll become clear later. Just trust me. Do you guys buy that, though, that if I label X, oh, sorry, and I need to put my theta there. The angle is still theta. So if I label things that way, then do you guys accept that the height would be the square root of x squared minus a squared? Okay. So the reason I labeled it backwards there is because I want to sort of think of it as there's really two algebraic situations I could find myself in. Variable squared minus number squared, or number squared minus variable squared, right? One or the other. What's the third algebraic possibility? What about if I have a plus in between? Okay, and that corresponds to where you know both legs, but you don't know the hypotenuse. Okay, does that make sense? If we've got two terms, squares, so we've got x squared and we have a squared, we could have both of them be plus, one of them be minus and the other be minus, or the other way. They can't both be minus because then that doesn't work in geometry. Okay, but we could have that, right? No. Those are the three situations. The bottom one is the one that we used in our example here. Okay, now let me draw all three of these triangles again, and I'll draw them slightly bigger. Okay, so this was one situation. Give me a trig function that's as simple as possible that comes from that triangle. Well, what are your options for your trig function here? Well, there's 6 to pick from, right? What's the simplest expression involving a trig function of theta that you can come up with here? Yes. Bingo. Okay. Tangent of theta, in this case, is the simplest one that you can write down. Now, can you write down sine of theta in terms of all those terms or cosine? Yes, absolutely you can. But that's the simplest of all of them. And if I solve that for x, then I get my substitution. Okay, so the moral of the story is if you have a problem that involves terms of the form x squared plus a squared, possibly with the square root, possibly with other powers, then the trick is to let x equals a tangent theta. Okay? All right, now the next one. Well, okay, think about without the square root, it'd be like that thing squared, right? So you can think of the square root squared as being just the nothing, right? So it would just be that, yeah. Okay. So yeah, the square root itself doesn't have to appear in your actual problem. It could be any other power. So like, for example, sometimes you'll run into things to the 3/2 as a power, right? Well, you can think of that as the square root cubed. Yes? Yeah. So, yeah, and when we look at some more examples, I think that'll be a bit more clear, although how time flies when you're having trig. Okay. The next situation we said we had was, oh God, that is the worst looking triangle ever. Have you guys seen that picture where it's like drawing a horse for the semester? Yeah. And drawing a horse. Let me see if I can find it because this is how I sort of feel. Um, Here we go. Yeah. Okay. It's how I sometimes feel when I'm teaching. Okay, so this situation we had the A here and the X there, and then the height was, and give me a simple trigonometric expression for involving theta. What could we do? What would cos theta be? Right? Adjacent over hypotenuse. And so what would x be? Okay. So the simplest expression I could write down there is the cosine of theta, or equivalently the secant of theta. And if I solve that for x, then that would give me the substitution x equals a secant of theta. Okay, is that okay? And then finally, the situation that we saw a moment ago, but now we're going to be a bit more general with it, which is if we have theta here, and I said I had x there and a there, then this would be square root of a squared minus x squared. And so we'd have, what's the simplest trig function in that case that we can use? A sine of theta. Okay, so there we go. So those are the three substitutions, and they will do any of these trig substitution problems. Okay, and uh, I've managed to run us out of time. I'm sorry about that, but okay. So the what you want to see then are some more examples of this. So if your problem involves square root of, or rather, the difference of two squares, one of them's a variable and the other one's a number, you're either going to use secant or sine depending on who's plus and who's not. Okay. And then if they're both plus, then you use the tangent one. And yeah, I guess we'll look at some more examples of this later. Okay, good for now anyway. All right. Well, I'll quit the stream here. If you guys have some questions, let me know. I got census taken care of, and I've got things to hand back to you. So, all right, I'll quit the stream here and see you guys whenever.